This is Dr. Jack Jackson, and this lecture is our second in our series of lectures on descriptive statistics. In this lecture we'll be dealing with measures of size. By this we mean not only the size of the sample or the size of the population, but also size of the various parts. We'll also be looking at different ways to represent data graphically as well as with tables. So we'll be looking at counts, population size and sample size, also tables of all values, frequency tables, relative frequency, and cumulative relative frequency. We'll also be talking about different kinds of graphs: stem and leaf plot, dot plot, sometimes called a line plot, circle graphs, sometimes called pie graphs or pie charts, bar graphs, histograms, Ogive and Pareto diagrams. So we'll be looking at all these different types of representations of data. To start out, we'll talk about just a basic measure of size and what letters we use for that. The population size is denoted by a capital N, and this is the total number of items in an entire population. Oftentimes, however, we will not know that. Very often we'll only have a sample that we're looking at. And so we'll use lowercase n for the sample size, the number of items in the sample that we are examining. So we'll always reserve these letters n, lowercase for sample size, uppercase for population size. Many times that we will be looking at tables. Tables are the simplest way of representing data, and if it has various variables of interest, then we may organize it or sort it according to any one of the variables of interest. For example, we're getting ready to look at a table of some data about U.S. presidents. And currently it's sorted by the order that they served in their office. But it could be sorted by any of the other variables in the table. So here's the first part of the table with the first 5 presidents. Notice we have lots of information here, the order that they served, and that's the order that we have the table sorted. We could also sort it by alphabetical, by their first name or by their last name. We could sort it by their party. We could sort it by their state that they lived in, or their birth date or death date or religion, inauguration date or death age. We could do any of these categories. Notice that we do have titles at the top and information down the columns. Now, frequency is simply a count. So if we're counting the number of items in say a certain category within the data, then that would be called a frequency. If we're expressing that as a percentage of the total amount, then that would be the relative frequency. So of course, to find the relative frequency, you divide the frequency by the sample size if it's a sample, or if it's a relative frequency within an entire population, then you divide the frequency of the category by the population size. Cumulative frequency is sort of a running total that gives you the frequency of values less than or equal to a given value. It is possible to do a cumulative frequency from the top as well, from those that are greater than or equal to it. Usually we think of it from the bottom up. A cumulative relative frequency is just the cumulative frequencies divided by the total size of the sample, or population if we know that, to get a percentage form. So when you see the word relative, think percentage. Let's look at an example here. So suppose these are distributions of grades for a class, 2 F's, 1 D, 8 C's, 4 B's, and 3 A's, say on a particular exam. So notice the relative frequency is dividing all those by the total size. So if we think of this as a sample, the sample size is 18. That's the total amount of students, total amount of grades. And in each case we divide the frequency, which is how many occur in that category, by the total. So notice what this says, that 8 is the frequency of C's. That means that 8 students earned a C. 8 divided by 18 then, which we could reduce, for example, to 4/9, is the relative frequency, or approximately in percentage form, that's approximately 44%, rounded off to the nearest percent. If we think of cumulative frequency, then we're accumulating the totals. So the number that are at F or below is 2. The number that are D or below is 3, so we're adding the 2 and the 1. The number at C or below is 11, so we're adding 2 plus 1 plus 8 to get 11, or just add the 8 to the 3 over here to get the 11. And similarly, 15 at B or below and 18 A or below. So then notice the last cumulative frequency will be the sample size. Then we can get cumulative relative frequency one of two ways. We can either take the cumulative frequencies and divide by the total. So 2/18ths, or about 11%, is F or below. 3/18ths, or approximately 17%, is D or below, and so forth. Notice you can also get the cumulative relative frequencies by accumulating the relative frequencies. So 11% plus 6% is the 17%. 11% plus 6% plus 44% gives you the 61%, and so forth. Notice the cumulative relative frequencies always end up at 100%, just like the cumulative frequencies always end up at the sample size. So it gives you a good example of frequency, relative frequency, cumulative frequency, and cumulative relative frequency. Another way that we can represent data in sort of a graphical but also numerical table form is what's called a stem and leaf plot, finally we'll end up with an ordered stem and leaf plot. It is a data table of all the data values in order. The stems represent the first digit of the numbers, and the leaves represent the last digits of the numbers. There's one leaf for each data value, but they will often share a stem. We can start this with an unordered plot and then order it, and this gives us a way of sorting the data in order. So let's look at an example. So if we look at the example of the ages of U.S. presidents, now this is going on the full table for which you saw the five first rows earlier. And by the way, the full table is in the end of our project that we worked on in this class. So this is the final result of an ordered stem and leaf plot. So notice the stems are the tens digits of the age and the leaves the units digits. So this says we had one president who was inaugurated at the age of 42, one at the age of 43, one at the age of 46, another one at the age of 46, for a total of two 46s, two 47s, a 48, two 49s, and so forth. So notice that we had a lot more in the 50s, about equal amounts in the 40s and 60s. None below 40, none above 69. Okay, now one way we could do this as an unordered stem and leaf plot would be to start and notice perhaps that we had presidents, by quick looking at the data, we had presidents with ages in the 40s, 50s, and 60s at the age of our inauguration, so we could start with those stems and simply go through here and write down the leaves in the order we came to them. So starting with George Washington, put his age on here, and then go to the next Adams and so forth. And then at the end, after we have the unordered plot, then we could turn around and put it in order. A dot plot gives us a nice, more visual, graphical way of representing all of the data points. Sometimes this is also called a line plot, although I prefer the term dot plot. It does graphically display every single data value. There will be a dot for every data value. It starts with a horizontal number line extending at least from the minimum to the maximum, possibly beyond, and you have one dot per data value above the corresponding value on the number line. So what happens if we get more than one dot at the same data value? Well, then we stack those dots vertically above that spot on the number line. And we can build this up one dot at a time as we come to the data, and we end up, we'll end up with the full dot plot. And this is a very useful way of illustrating the graph and also various characteristics about the graph. So we'll be coming back to the dot plot throughout these lectures to see these data values. So here's the dot plot of the age of inauguration of all the presidents. So the first president, George Washington, we would have put one dot there. Then the next at his age. Then the next one we would have come up with Adams and put a dot for his age. And then the next one, and then the next one, and the next one. And eventually at some point we're going to have duplications, and then we stack the dots up evenly spaced out like this. Notice that we have a full number line, including the empty spaces if there are some. This gives us a full picture of every age of inauguration, at the first inauguration of every one of the presidents. Now we have lost some information that was in our chart. It says nothing about their religion, it says nothing about their party, doesn't even have the names that go with each dot. But it does keep all of the information in terms of which ages that we have, and it gives us a nice visual representation of how they're spread out. A circle graph, or sometimes called a pie chart, is used for nominal categorical data, and it's used to show parts of a whole. We take a circle, and from the center of the circle we slice out little circular sectors or wedges or slices of pie, and those, both the area of the sector and the size of the central angle, are proportional to the frequency. To find the central angle, you can take the relative frequency, remember it's a fraction or a percentage, and multiply by 360 degrees, which is 360 degrees is all the way around a circle, and that will give you the central angle. Now, of course, to do this by hand, you're going to need a compass or something else to make a circle where you can mark the center. You're also going to need a protractor. You're also going to need to first figure out what all the central angles are, and then very carefully draw it in. Of course, computer technology will also do this for us. The labels on the graph will include the label of the category, sometimes given in a legend, sometimes given on the slice itself. And then it will also give you either frequencies or relative frequencies or both as well. Here's an example of the parties of the U.S. presidents. Notice that we have several different parties represented here, 6 different parties over time. By far the biggest are Republican and Democrat, but then some of the precursors of these parties, the Democrat, Republican, Federalist, Whig, and Unionist, were also there from time to time. So for example, we can look at the Democrats. We notice that there are 14 Democratic presidents, which makes 32.6%. So the 14 is the frequency, the 32.6% is the relative frequency. And then we have the category named Democrat. We also have the categories listed off to the side, and ideally the wedges would be different colors. Again, this is categorical data, so there's no inherent order to these wedges. They're just placed in there. But we can see visually something about relative size. Now, anytime you have a circle graph, you can also have a bar graph. We can have bars with these same heights, and many statisticians would say that a bar graph is just as good or even better, and perhaps a more efficient way of representing this data. Nevertheless, circle graphs or pie charts are very popular. A pictograph uses pictorial symbols to represent a quantity of items. These are used because they're visually appealing, but they contain exactly the same information as a bar graph, and they're harder to read. So really, you should always replace these with the bar graph instead of the pictograph. And if there's something you want to do with that to make it look more visually appealing, you can do that by changing the background colors, adding other graphics, and so forth. Here's an example of a pictograph where this little car represents 4 cars, and say we have a certain class that has American-made cars, and we see that we have some of them had Ford, some General Motors, some Chryslers. Well, how many are these? Well, when the car is whole, it's not so bad to see, but notice that we have to also represent these fractions of cars here. It's cute, but not as easy to read. A bar graph, and a histogram is a special kind of bar graph, the output variable should be ratio data, for example, frequency or relative frequency. But the input variable can be nominal categorical data or any higher level as well. The heights of the bars represent the output values, for example, the frequencies or possibly relative frequencies. The input values may be individual data points, or we can group similar values together. For example, in the presidential data, we could group, say, all of the 40s together, the 50s together, and the 60s together in terms of the age at initial inauguration. Or we could further subdivide it: early 40s, late 40s, early 50s, late 50s, early 60s, late 60s, and maybe split it like that into multiple bars. We can arrange this either vertically or horizontally. A histogram is a bar graph, but the output values are either frequencies or relative frequencies. So some things to remember about bar graphs: they should always start the bar at 0, and they should not have any breaks in the output axis. Always make the bars the same width, so that areas and heights are proportional to frequency, both areas and heights. The bars will touch if the input is continuous data that has been rounded and grouped. Okay? But the bars do not touch if the input is nominal or discrete data. Avoid three-dimensional bars. Even though they visually look cool, they're hard to read and may be misleading. Make your graph visually appealing in some other way. So lots of things you can do with that. Change the colors, change the textures, change the backgrounds, change the fonts, change the patterns on the backgrounds and the bars. There are lots of ways you can make your graph look pretty or look visually appealing to your audience without sacrificing clarity. So this is why we prefer a bar graph over a pictograph, and that's also why we prefer to not use a 3D bar graph. On the circle graphs especially, we do not like to use a 3D version of those because it definitely distorts things. So here's the same information that we had with the pictograph earlier of a bar graph for General Motors and Chrysler. But now notice this is much easier to read. Even without the numbers on tops of the bars, you could read off the values of this much easier, much more easily than you could in the pictograph. Here's a histogram of the parties of the U.S. presidents. This is the same information that was given in the circle graph earlier, and we still get the message that there are more Republicans than anything else. Next would be Democrats, and then the other parties were smaller by comparison. We can also group frequency histogram. Here's another one where we grouped into the early 40s, late 40s, early 50s, late 50s, early 60s, late 60s. They're actually divided into 7 categories, and these numbers that you see here at the bottom are the center of the category, and then they go up and down centered on those. One could adjust this different ways. This was a way that Minitab just defaulted to produce this table. Notice that most of them, the presidents here, you can see the biggest group, not most, but the biggest group was around 56. Okay, plus or minus some that they're grouped together. An ogive is a cumulative relative, or the cumulative relative frequency or cumulative frequency, either one, broken line graph. So we can always start it at 0, 0, or sometimes you'll see it starting at the first data value. And we will place dots there at each data value, comma, the cumulative frequency or relative frequency, cumulative relative frequency. There'll be a dot and connect the dots with straight line segments. So it'll start at 0 and basically end at the sample size, or start at 0 and end at 100%. We'll see an example of this below in a Pareto graph. So Pareto graph is used for nominal categorical data. It's a combination of two things. It's a frequency bar graph, and the bars are placed, though, in order from the highest bar to the lowest bar. Now remember, if it's a nominal data, there's no inherent order, so it is totally okay for us to reorder the bars. You wouldn't want to do this with ordinal data because there's an inherent order in ordinal data. So you'd place the bars in order that's there for ordinal data. But for categorical data, nominal data, there is no order, and so we will place them in the order from highest to lowest. So the bars will sort of stair-step down. Sometimes you group things in the others category. Sometimes you can place the others category last, even though if it's slightly higher than the one before. Some people do that. But if the others bar is too high, very high, you shouldn't have it that way. You should go ahead and break it apart. But a Pareto graph, sometimes people will say just that bar graph is the Pareto graph. But most of the time a Pareto graph also includes an ogive on top of that. So we'll take a look at that at an example. So the output scale may either be frequency or relative frequency for the bar graph, and always is cumulative frequency or possibly cumulative relative frequency for the ogive. You can include both by placing scales on both sides of the graphs. One a percentage scale, one an actual count scale. So, here is a Pareto chart of the religion of the U.S. presidents. Notice we start the highest bar with Episcopalian. Looks like we had 11 of those. Then Presbyterians, 6 of those. Then Methodists, okay, at 4. Unitarian at 4. 3 Baptists, 3 Disciples of Christ, and so forth. So these bars are descending in order. Then you have, so that's the bars, the heights of the bars are actually the frequencies, which you can read where it says count on the left, that's the frequency. Or you can see the percentages, which is the on the right, that's going to be the relative frequency. But then we also have this little red broken line graph that goes up, and it starts at 0, 0, and then the next one is at the first Episcopalian, comma, 11. Then it's Presbyterian, comma, well, it's at we see the cumulative amount there, which is at 40% overall. Okay, and so we keep going up like that. Now this is often used in a manufacturing situation, where instead of, say, religion, this would be causes of a problem. So we might have different defects that show up, and the biggest bars would be first. This is really nice because this allows you to focus on what they call the significant few rather than the trivial many. So oftentimes you'll find that the first 2 or 3 or 4 bars will account for the vast majority of your problems. So you might be able to isolate just 2 problems, and that accounts for well over half of your overall number of defects. So by isolating those, you can see that and focus on what's the problem.